is determined by the choice of the Q-exact definition. Okay, so let's try to compute this bonding determinant from the chiral multiplet in some representation R. All you have to do is to expand this deformed action, in our case, the kinetic Lagrangians, up to quadratic orders in the fluctuation field. Then, all we need to do is just to compute the eigenvalue of these differential operators acting on the bosonic fluctuation field and the fermionic fluctuation field. Here, this D represents the covariant derivative under this monochrome background, which is given by this expression. Well, it's a standard analysis. Then one can show that this bonding determinant from the real scalar field in this chiral multiplet is given by this expression by doing the spectral analysis. And one can show that this bonding determinant from the fermionic field in this chiral multiplet is given by these expressions. And as you can see, there is a huge cancellations between this boson and fermion eigenmode. But we are still left with infinite number of unpaired eigenmode, this boson and fermion eigenmode. And at the end, one can show that this bonding determinant from this chiral multiplet carrying some electric charge rho is given by these expressions. So here, the fact that there is a huge cancellations between this boson and fermion eigenmode implies that there must be some kind of index theorem which helps us to compute this bonding determinant without doing the spectral analysis. However, because of this fact, we are still left with this infinite number of unpaired eigenmode. This implies that this is not the index theorem for the standard elliptic operators, but we have to use the index theorem for transversally elliptic operators. But today, I'm not going to talk about what this index theorem is. And anyway, we can do this full spectral analysis and obtain some result.
So this Calabi multiplet, is it necessarily massless, or could it have a...
We can introduce the mass term too, but it depends on the twisted mass term only. I mean, the complex mass term in the superpotential, but the two superpartition function doesn't depend on that complex mass term. Any other questions? All right. So as you can see, this infinite product is obviously divergent. So in order to get some final result, we need to regularize it. And today I'm going to use this zeta function regularizations to get some final answer. And at the end, one can show that this exact two-square partition function of this two-dimensional supersymmetric gauge theory is given by these expressions. W is the Weyl group of the gauge group. B is the quantized flux on the two spheres. And this is the ordinary integral over vacuum expectation value of one of the real scalar field in the vector multiplet. We have a classical action contribution here, where C is a phi parameter, theta is a two-dimensional theta angle, and finally, we have one determinant from the vector multiplet and chiral multiplet, which are properly regularized. Here, alpha denotes the positive root of the gauge group, rho is the weight of the representation R with the chiral multiplet, and finally, this one Q represents the U1R charge of this chiral multiplet, and this is an exact answer. And as I told you earlier in this talk, as you can see here, this two-square partition function is really independent of the gauge coupling constant and the superpotential parameters. Fine, but some of you may wonder whether this finite piece of this two-square partition function depends on the choice of the regularization scheme. In other words, if I use a different regularization rather than this zeta function regularization, it is not clear whether we obtain the same answer for this finite term of the two-square partition function. So to understand and to answer these questions, let me carefully consider this UV divergent structures of the sphere partition function.
Finite term, you're saying other than the Z1. The Z1 loop is also finite once you regularize.
Yeah.
You can have one loop determinant again. Just does the integral converge here?
When a phi parameter is non-zero, many cases it's convergent. But sometimes there is an issue about the convergence too.
Yeah.
Actually, this is just probably So in other dimension, do you also have this issue with regularization?
Yes. In
Right.
3 dimension, no.
Uh-huh.
I will discuss about
Yeah,
that part.
okay, yeah, because in hard, yeah, because I'm just curious, 'cause ultimately you're gonna get this Kato potential business, right? And this
Yeah, I will
Kato
come to that part
transformation.
in
I'm
a
just
second.
curious in that.
Yeah, so for simplicity, let me just focus on the 2-sphere partition function and 3-sphere partition function in 2 base law. And their UV divergent structures is given by these expressions. Here lambda is the UV cutoff scale. T is the some marginal coupling constant of the 2-dimensional CFT and the 3-dimensional CFT. Here I just focus on the conformal field theory case. Well, so in order to study this regularization scheme dependence in a systematic manner, it is very convenient to promote this marginal coupling constant to some background field, as Zowar Gomakowski explained. And then we need to classify all the possible counter term or contact term of this background field and the background metric. And then we need to require this contact term to preserve some symmetry of the given theories. In particular, diffusion invariance. Right? So let me first start with this power law divergences. Okay, so it is well known that this power law divergence can be easily cured by adding some local counter term. It doesn't have any physical meanings. For instance, this quadratic divergence in these 2-sphere partition functions can be easily absorbed completely by this counter term. This cubic and linear power divergence in these 3-sphere partition functions can be also cured by adding these following counter terms, where this R represents this the scalar curvature on the background manifold. So this is well-known story. But in even-dimensional space-time, the sphere partition function also contains the logarithmic divergence, which is highlighted in these expressions. And it's also well known that this logarithmic divergence cannot be cured by any counter term. In other words, this logarithmic divergence is independent of the choice of the regularization scheme. Therefore, it must have some physical meaning. Indeed, one can show that this logarithmic divergence reflects so-called the trace anomaly or bi-anomaly of the conformal field theory in even-dimensional space-time. And furthermore, using this best-Schumann consistency condition of that anomaly, we can show that the coefficient of this logarithmic divergence is independent of the marginal coupling constant. It's just constant on the conformal manifold of the given conformal field theory.
Does it agree with the C function away from the fixed points?
Here I just talking about the marginal coupling constant.
Yeah, but if it generally if you have some RG flow being different theories, and you can compute the sphere point function and look at the C as a function of the scale. And does that agree with the C function?
You mean even that case C is independent of the coupling constant?
No. I'm saying that there's some non-trivial RG flow, so C will depend on it will be a function of scale. It changes from one theory to another.
Yeah, that's true.
And does it agree with the homological C function?
Agree with what?
With the homological C function, away from the conformal fixed points.
I think so. No.
I don't know. I'm just curious.
Sorry, yeah, maybe. I don't know the exact answer for that. Okay. And this constant C can be identified as the central charge C in the 2-dimensional CFT and the central charge A in the 4-dimensional conformal field theory, which is associated with this Euler density in this anomaly equation. Okay, let's now move on to this finite term in this 2-sphere partition function and 3-sphere partition functions, and discuss their dependence on this choice of the regularization scheme. Well, in fact, let me start with this even-dimensional space-time. In the case of this non-supersymmetric theories, actually one can show that this finite term in this sphere partition functions can be completely absorbed by this local contact term, which is given by these expressions, where E represents the Euler density of the background manifold. This implies that this finite term in the sphere partition functions is totally ambiguous, and it doesn't have any physical meaning. However, when you consider some supersymmetric theories, we have to require that this contact term should preserve some symmetry, supersymmetry, in this case SU2/1. And this requirement strongly constrains the possible form of the contact term we can add to the theories. In fact, one can show that this finite contact term preserving this SU2/1 supersymmetry is given by these expressions, where E represents the twisted chiral density superspace measure, capital R represents the twisted chiral curvature superfield, and F is an arbitrary holomorphic function of T, where T is the twisted chiral superfield whose lowest component can be identified as a background discoupling constant T. Here I just decompose this background field for this coupling constant into holomorphic and anti-holomorphic things. And this finite contact term tells us that the finite term in this sphere partition functions is ambiguous in a very particular way, such that which can be summarized by this equation. It's ambiguous up to holomorphic function and its complex conjugate. And this ambiguity is known as the Keller ambiguity. So because of this fact, one can show that the second derivative of these two sphere partition functions, d and d bar, acting on the log of these two sphere partition functions, can have a definite physical meaning, which is independent of the choice of the regularization scheme. And as I will show you in the afternoon talk, this will compute the homological metric on the conformal manifold of 2D and equal to superconformal field theories.
So the rescaling of lambda is a special case of this F. F equals R.
Any other questions?
Sorry, how is the twisted chiral curvature superfield defined? The R?
Definition of it?
You're talking about the analog of the scalar curvature on the
superfield, superfield curvature. I mean, there is a chiral superfield curvature.
Okay, so what happens to that R in computing going from that action to F?
So here we need to integrate over some. So where is this one? So you are asking how to get from here to here?
Yes.
Just integrate over this space.
Yeah. Well, so what happens to the epsilon R? I didn't understand what you did there.
So when you integrate this quantity over this space, superspace, you get some constant.
So you say R is some superfield analog of the scalar curvature on the supersphere?
Is that answer to your question?
I still don't know the definition of that thing
Yeah.
is, but
Yeah, I will show you.
okay.
Yeah. Okay. So yeah.
So the simplest example is what? Tau is something like, it can be a complex F5 prime.
Yes. Yes. T. Yeah. The background field for this F5 parameters is theta, two-dimensional theta.
So there's any other good examples of those things?
Any marginal coupling constant can be preserving this SU2/1 can be promoted to twisted chiral superfield. Okay.
So if you're speaking of a conformal theory, one should not refer to the metric structure on this 2D surface, but just the Riemann surface structure. So how would you define?
Here I just impose this SU2/1 supersymmetry only. The regularization cannot preserve the conformal structures. That the most thing we can require is this massive part of the superconformal algebra, which is the SU2/1. Does that answer to your question?
What was the example I was asking about that?
Yeah.
If you change the Liouville factor, everything changes by just a term proportional to the central charge.
Yeah.
Which will leave, since that's independent of the moduli, it will leave this derivative as
Yeah. Okay. So for completeness, let me discuss about this finite term in the odd dimensional space-time. Well, in the 3 dimensions, the only possible finite contact term you can add to the theory is a three-dimensional gravitational Chern-Simons coupling, which is given by these expressions, where omega is the spin connection. And this gravitational Chern-Simons couplings, as you can see, is purely imaginary. So at least the real part of this finite term of the three-sphere partition functions is independent of the choice of the regularization scheme, and it must have some physical meaning. And indeed, it was proposed by Daniel Jeffries that these quantities will measure the number of the degrees of freedom, the three-dimensional quantum field theory, which will decrease along the RG flow monotonically, which is the kind of three-dimensional analog of the homological seed theorem. And now this conjecture is known as the F theorem. And later on, this real part of the finite term of the three-sphere partition function can be identified as an entanglement entropy with circular boundary.
And in this case, the real part of the three-square partition function is meaningful even without supersymmetry.
Yes, yes.
Unlike the two-dimensional case.
Unlike the two-dimensional or four-dimensional. Four-dimension has such an ambiguity too, so it has a physical up to Keller transformation again. If you require the supersymmetry, n equal 2.
And it's completely unphysical.
Yeah.
Without supersymmetry.
Yes. And using this conformal order identity, one can further show that this real part of this finite term is three-sphere partition function is independent of the marginal coupling constant. Therefore, it has to be constant on this conformal manifold of the three-dimensional conformal field theories. Then what about this imaginary part of the imaginary part of the finite term in the three-sphere partition function? Well, this analysis is a little more involved. And roughly speaking, this gravitational Chern-Simons coupling, the Chern-Simons level is quantized. So at least the fractional piece of this imaginary term, imaginary part of the finite term of the three-sphere partition functions, has some physical meaning. But today I just don't want to. I will not tell more details about this physical meaning of this imaginary part today.
And is this counterterm actually supersymmetric?
This one? Yes, you can supersymmetrize it. Yes. All right. So far we discussed that this logarithmic divergence of these two-sphere partition functions is independent of the choice of the regularization scheme. Therefore, it must have some physical meaning, which reflecting this biosymmetry, anomaly, and so on. We also discussed that this finite term of the two-sphere partition function is also physical of the Taylor transformation. So I think it's important to revisit this boundary determinant again to see how this logarithmic divergence looks like. So this is the starting point, the boundary determinant from the chiral multiplet carrying electric charge rho. And from these expressions, one can carefully read off this logarithmic divergence, which is given by these expressions. And indeed, these first two terms can be understood as a contribution to the central charge of this two-dimensional CFT from this chiral multiplet carrying UNR charge Q. And the last term in this bracket can be understood as a boundary correction to the Fi parameters. Of course, for the theory having ion fixed point, this boundary correction to the Fi parameter will eventually cancel out. So collecting all this fact, one can show more. Collecting all this fact, the more precise form of this two-sphere partition function is given by these expressions. Now we have some prefactor that depends on this UV scale explicitly. And from this prefactor, we can read off the central charge of the IRCFT, which is given by these expressions. The dimension of the representation R of the chiral multiplet times 1 minus Q. This Q is the UNR charge of this chiral multiplet, minus dimension of the gauge field. And this formula can be nicely summarized into the simple form, which is a trace of R, where R is the vector UNR charge, where the trace is performed over all the Fermi equivalent theories. And this formula perfectly agrees with what Silverstein and Wittun and Uri and Tong obtained about 10 years ago. And in the integrand for the massive theory, this Fi parameter is now replaced by the renormalized Fi parameters, which is given by this expression. But in the case of the gauge theory having I a fixed point, this boundary corrections just cancel out. So this is the more precise form of the two-sphere partition function of the supersymmetric gauge theories. Any questions? Okay, so let me now move on to different type of supersymmetric theories in 2 dimensions, which is the Landau-Ginzburg theory. This Landau-Ginzburg theory involves, let's consider this Landau-Ginzburg theory, which involves this twisted chiral flat, whose interactions can be described by this twisted superpotential W. Here we choose the same supercharged Q for the Suji localization technique. So inside is SU2/1, and we choose the connected Lagrangians for this twisted chiral multiplet as our Q-exact definition. And then one can show that the supersymmetric setup point where this path integral can be localized into can be described by these simple configurations. The complex scalar field Y in this twisted chiral multiplet can have some arbitrary constant value of the 2 spheres, and all other fields in the theory should vanish. And then one can further show that this one determinant around the supersymmetric configurations is trivial in the sense that this one determinant doesn't depend on the supersymmetric setup point configuration code. So as a consequence, this 2-sphere partition function of this Landau-Ginzburg theory can be written as the following simple form. This is just an ordinary integral, and the integrand depends on this twisted superpotential W. And it's important to note that this exponent here is purely imaginary. So this is the exact answer for this. This is the exact two-sphere partition function of this Landau-Ginzburg theory. So any questions so far?
Yeah, the integral doesn't appear well defined. So
Sometimes it's not defined. Sometimes it does well defined.
how? I mean, how do you define it? I mean, you have to say how you.
Mm-hmm.
Well, I mean, it's oscillatory and.
It's oscillatory, yes. I will give you some example later. You will in the next section.
Well, it sounds like you.
So in general, yes, there are some problems in the convergence. It's a formal expression, it isn't. All right, so any questions? No. Okay. So let's now move on to the application of this exact result in the 2-dimensional theories, especially in relation to application to the string theory compactifying the Calabi-Yau space. So let me first briefly review the basic things about the string compactifications. Today I mainly focus on this type 3 string theory compactified on this Calabi-Yau manifold. So here, so I will consider this type 3 string theory in Calabi-Yau 3 manifold, whose low energy effective theory can be described by this 4D n equal 2 supersymmetric theories. And we can also study this 4-dimensional physics from the worship point of view, which is the nonlinear sigma models, whose target space is this Calabi-Yau manifold, which is the conformal field theories. In this Calabi-Yau space, we have so-called Keller in the complex structure moduli space, which will determine the size and the shape of this given Calabi-Yau manifold. And this moduli space will lead to various Metzler scalar fields in this 4-dimensional theory from compactifications. In particular, this Keller moduli parameter will give us a Metzler scalar field in the vector multiplet. From the worship point of view, this Keller and the complex structure moduli space will define the space of the marginal coupling of the corresponding 2-dimensional superconformal field theory, n equal 2. For many purposes, it's very important to understand and know the precise kinetic energies and precise potential energy of these 4-dimensional supersymmetric theories. So in order to do that, we have to compute the quantum correction to the metric on this modular space of the Calabi-Yau space. In the language of the 2-dimensional CFT, this metric is nothing but the jamological metric on the space of the marginal coupling constant, marginal couplings, which is well known to receive the various quantum corrections, especially non-perturbative quantum correction generated by these Gaussian instants. In general, this is a very difficult problem, computing this Gaussian instant correction to this metric exactly. But as you know, the mirror symmetry has provided a beautiful solutions to this problem, computing this Gaussian instant correction exactly for some examples. However, unfortunately, there are not so many known examples where you can do a systematic way to construct this mirror descriptions for a given Calabi-Yau manifold. So people would like to find more direct and more powerful method to compute these Gaussian instanton corrections without relying on these mirror symmetries.
When you say quantum metric or moduli space, from the point of view of string theory, it's the alpha prime corrected. Right?
Yes, so that's the achievement. Okay. And as I told you in the afternoon talk, this two-sphere partition function will provide such a direct and powerful method to compute this Gaussian instanton correction to this homological matrix. But in this morning talk, let me first investigate this mirror symmetry from this two-sphere partition function point of view. So let me first explain why this mirror symmetry has been so useful to compute this Gaussian instanton corrections to the metric, the homological metric. Well, in late 80s and 90s, people found that the Kähler moduli space of certain Calabi-Yau manifold can be mapped to the complex structure moduli space of the other Calabi-Yau manifold under the mirror map. And this is very nice because although the metric on this Kähler moduli space can receive various quantum corrections, including the non-perturbative quantum corrections, the metric on this complex structure moduli space doesn't receive any quantum corrections. So in other words, the quantum problem on the one side, computing these Gaussian instanton corrections, can be mapped to the classical and purely geometric problem, or we can solve relatively easy. So that is the reason why this mirror symmetry was so powerful. And the question is whether or not we have a systematic method to construct these mirror descriptions for a given Calabi-Yau manifold. And the answer is yes, for some class of the Calabi-Yau manifold, which is known as the complete intersection in the toric varieties, and this method is known as the Horibaffa mirror map. More precisely, we have a systematic method to construct the mirror descriptions of a given abelian supersymmetric gauge theory in 2 dimensions in terms of the Landau-Ginzburg theories. And here, this abelian gauge linear sigma model will describe this particular Calabi-Yau manifold with a complete intersection in the toric varieties. So let me first explain 2 important ingredients to devise this beautiful method, Horibaffa method. One is the T-duality, which is also known as the scalar-scalar duality in 2 dimensions, which can be summarized by the simple equations, where phi and y are real scalar fields in the 2 dimensions. In the supersymmetric setup, the scalar field can be identified. One of the scalar fields, say phi, can be identified as a phase of the complex scalar field in this chiral complex, which can be dualized to another scalar field, y, which can be identified as an imaginary part of this complex scalar field in the twisted chiral. In other words, under these T-dualities, this chiral multiplet and the twisted chiral multiplet get exchanged to each other. Another important ingredient for this Horibaffa mirror map is this non-perturbative, dynamically generated twisted superpotential W for this dual variable y, which is given by this e to the minus y. This potential is generated by the instant. And then, when you try to describe this low-energy effective theory of this abelian supersymmetric gauge theory in 2 dimensions in terms of this dual variable y, together with this twisted superpotential, you finally end up with some Landau-Ginzburg descriptions, which is a mirror description to this abelian gauge linear sigma. So this is the basic idea of the Horibaffa mirror map. So let me consider the simplest example, which is the U1 gauge theory that involves some n chiral multiplet whose electric charge is QA satisfy this anomaly theory conditions. This abelian gauge linear sigma model will flow in the infrared to the non-linear sigma model whose target space is non-compact to a Calabi-Yau manifold. When you use this Horibaffa mirror map, we can easily construct the Landau-Ginzburg theory, which is a mirror to this supersymmetric gauge theory. And this Landau-Ginzburg theory involves n twisted chiral multiplet satisfying these periodicities, and the twisted superpotential is given by this one. So this is the Landau-Ginzburg theory mirror to this gauge linear sigma model. Then let's now compute the two-sphere partition function of these 2 theories and see whether these two-sphere partition functions agree to each other.
So So here the non-linear model is supposed to flow to a particular point in the moduli space of the CFT.